Alright, so today we're going to be talking about the Claisen condensation and Dieckmann reactions, both of which are just sort of variations of an allyl reaction, but involving esters. So the same steps basically occur, where we have our initial deprotonation of the alpha carbon, which in turn forms our enolate, which will then perform nucleophilic acyl substitution on our carbon electrophile. To show that as an example, what we can do is just draw a simple ester, where our leaving group will be the same as our base that we used to deprotonate. And what that does is basically just allow us to avoid any side reactions going on. So now we have our base. We will also use the conjugate acid as our solvent. So what will happen is we will first deprotonate that alpha carbon, which we will mark in red, with our base, which will cause these electrons in this bond to flip up onto our alpha carbon, forming our enolate. And in this reaction, our starting material will react with itself. If it did not react with itself, that would be a crossed Claisen condensation, which we can show later, but for now, this will just be a simple condensation where it reacts with itself. So basically, we would have another one of our starting materials, our starting esters, over here, which will undergo nucleophilic acyl substitution with these electrons right here. They'll go up and flip up here, causing our double bond here on the oxygen, on the carbonyl, to flip up towards the oxygen, giving it a negative charge. And as you might already notice, this right here will be our leaving group. So when this occurs, we will form our intermediate. This is where the nucleophilic acyl substitution took place. And our leaving group will be over here. So what happened here is one of the lone pairs on this oxygen will flip back down, reforming that double bond, and these electrons will go back towards our leaving group. So what we will have is our Claisen condensate with one of our leaving groups as base. So with that negative charge, which leaves us to our quenching step, or our mild acidic workup, which basically will bring about the protonation of our base and our leaving group, which are the same in this case. So what will happen here is, to prevent any side reactions from occurring or any further deprotonation, we can basically just add acid and water, which will then react with our base and leaving group, which is right here. And that will cause the protonation of this, where we will get ethanol. And that kind of does it for our not crossed, just simple Claisen condensation. This will be our end product right here. So to recap, we first have the formation of our enolate. Then with that partial positive charge on our carbonyl carbon and that partial negative charge on the oxygen, our carbon nucleophile right here will react with our carbon electrophile, which is over here, forming this product, which then undergoes a elimination where that leaving group leaves and then is protonated, and then we have our final product. And this reaction can occur on an intramolecular scale as well, where it is instead called a Dieckmann reaction. So in a Dieckmann reaction, we have the exact same mechanism, but again occurring on a intramolecular level. So if we were to, let's say, have our ester, well actually two esters in this case, and our alpha carbon, which will be here, we'll mark that out in red, will basically be deprotonated the same way as it was last time. So we can also number these with that's number 1. Let's mark it here. This will be our second, third, fourth, and our fifth. So what will happen here is we'll have our other ester, which again has the same leaving group, and this will be deprotonated with our base, which we'll do the same as last time, our sodium ethoxide, and our solvent will be ethanol, again to avoid any side reactions that can occur with a different base and leaving group. And we can again draw our base deprotonating our alpha carbon. So now we have the following enolate. So now we have our carbon nucleophile, which is on the same molecule as the rest of it. We can now undergo nucleophilic acyl substitution intramolecularly, where we have our partial positive charge up here on our carbonyl carbon and the partial negative charge on the oxygen. And our electrons will move on over to form a ring intramolecularly. So now what we will have is the following intermediate, where we form a ring with 6 members, with this bond being at the carbonyl, or the former carbonyl, because this bond with these electrons, these pi electrons, flip up, giving this oxygen a negative charge again. And what will happen is those electrons are going to flip back down and cause our leaving group to leave. So what we'll end up with is the following molecule and the following leaving group, which we know will be protonated in our acidic workup to avoid any further reaction. So in this situation, we and in the other reactions, basically all forms of the Claisen condensation will create a beta keto ester, which is also called a 1,3-dicarbonyl compound. A beta keto ester. And what that means is that on all these molecules, these carbonyls, these are both right next to each other. They are at 1 and 3. So this is at the beta position, this being the alpha position right here. And this is also called a 1,3-dicarbonyl compound. And this reaction can occur instead with 2 different molecules, in which case it is a cross-Claisen condensation. And we can just really quickly show that, where we have, let's say, one ester that we did before with our ethoxide leaving group, our hydrogens here, which of course will be deprotonated by our base, which will be the same as it was before, with ethanol as our solvent. And we deprotonate, level these electrons, form our enolate, but this time we can have instead a different molecule that will be our carbon nucleophile, carbon electrophile. So instead we can just draw, for example, let's just say we have another ester, but this time, so we have a butyl group going off here. We will basically undergo the exact same nucleophilic acyl substitution with our partial positive charge on that carbonyl carbon. And we'll get a different product than if we just reacted the two, or the starting materials together. The original starting material, this one. This bond will flip back down, as we know, with our leaving group being right here, and our butyl group kind of just going off here. These electrons in this bond will go up and cause our leaving group to leave, which will create our final molecule which will look something like this. By the way, this has a negative charge. With our leaving group looking like this, and in turn being protonated in our acidic workup. And that kind of sums it up for our Claisen condensation and Dieckmann reaction summary. So thanks for listening.